Welcome to this video lecture about Euler's number E along with its most important properties. It's primarily targeted towards those who are confronted with the stuff on a regular basis or are about to and want to improve their basic understanding. However, by starting from the very beginning and explaining every element of the reasoning, thereby recapitulating possibly faded knowledge, it should also be useful to a wider audience. The subject is covered in full, all the way from the definition of E up to Euler's formula. Its main focus is to provide the viewer with a proper conceptual understanding of the basics, in addition to the mathematical foundation. In all cases, the discussed subject is first made plausible before a more substantial demonstration is presented. The whole lecture consists of 4 episodes. This first one is about exponential functions a to the x in general, with their properties, from which the definition of the special number E will arise. In the process, some related issues will be recalled as well. In part 2, from that definition, a power series will be set up for the exponential function e to the x that will result in a close approximation for the value of E. The convergence behavior of this series will be paid special attention to. Next, part 3 deals with the properties of exponentials with complex exponents. The convergence trajectory in the complex plane will provide additional understanding of their behavior. Euler's identity will result from this. And in the fourth and final module, such complex exponentials will be connected to sine and cosine functions in the form of Euler's formula. A few examples of its usefulness will conclude this lecture. To be able to follow the explanations, you can do with graduate level high school math. Properties of functions in general, as well as the basics of trigonometry, exponentials and logarithms should be part of it. Further, elementary differentiation and knowing how to deal with a few standard derivatives is needed, together with applying the chain rule. Since the parts 3 and 4 of this presentation are all about complex numbers, you should also be familiar with them, at least to a reasonable extent. The power series that are used in a few derivations will be set up in such a way that no further specific knowledge is required. As mentioned before, the explanation starts from the very beginning, thereby compensating for the required prior knowledge having faded away over time. I will briefly introduce myself. My name is Wim de Valk and I'm a retired lecturer of electrical engineering at the University of Applied Sciences in Eindhoven, the Netherlands. During my active career, I've been teaching, amongst others, the subject of discrete signal processing that relies heavily on the number E. Through this video presentation, I want to share my personal understanding of its concept with anyone who may benefit from it. As was said in the overview, this first episode of the lecture will start with an introduction of exponential functions in general. Many physical processes show some kind of exponential behavior, so there's really a plethora of examples of them. Here we will observe the spreading process of an infectious disease, like corona for instance, in an early stage when immunity doesn't play a role yet. Next, it will be demonstrated that the derivative of an exponential function is proportional to the function itself. The value E follows from the premise that both are assumed to be equal. This module will conclude with some related issues such as logarithms, the inverse of exponential functions, of which the natural log serves as the counterpart of e to the x. Consider a single person infected by some disease taken aside from the whole of the population. Assume he or she is contagious for 1 week and will infect 2 other persons during that time. 2 is therefore the so-called reproduction number. At the end of the first week, the number of infections will have increased to 2. The next week, the 2 infections will each be passed on to 2 other persons, leading to 4 infections at the end of it. After 3 weeks, the number of infections will have risen to 8, then 16, 32, and so on. These numbers can be written as 2 to the x, with x being the weak number. The growth of the number of infections is obviously proportional to the numbers themselves, which is characteristic for an exponential relationship. As a result, for every equal amount delta x that x advances, in this case with delta x being 1 week, the belonging value grows by a corresponding factor. Here it's the factor 2. In the population as a whole, at the start of this period, the number of persons already infected is assumed to be N0. After 1 week there are 2 times N0 infections, after 2 weeks 4 times N0, next 8 times N0, 16 times N0, etc. With so many people involved, the infections can take place at any moment in the time. So the course of the epidemic can be expected to follow a kind of continuous curve rather than a succession of discrete numbers. Further, the epidemic doesn't start in the beginning of the period under consideration, but will have quite a history before. A week earlier n was half N0, 2 weeks before it was a quarter of N0, and so on. All in all, the infection progress function n of x, that is doubling by the week, possesses an exponential course. This curve follows the equation n of x equals N0 times 2 to the x. The factor 2 to the x in it forms a continuous exponential function with base 2. It satisfies the requirement for being a function, namely that for every different x value there is one unique y value. Exponential functions possess the very important property of their steepness, that is their rate of change, being proportional to their local value. To demonstrate this, the steepness of this function is graphically determined at a number of locations beginning at x equals 0. There, the tangent line to the function is drawn, whose inclination is equal to the function's local steepness. At a distance of 1 along the horizontal axis, the measured vertical difference represents the tangent line's inclination, that appears to be approximately 0.69 times N0. This is repeated for x equals 1 and 2, at which places the inclination equals 1.38 and 2.77 times N0 respectively. Notice that the successive measured inclination values 0.69, 1.38 and 2.77 times N0 possess the same relative proportions 1, 2 and 4 as the function values themselves at those locations. The so constructed line segments that indicate the function's steepness are now moved to the horizontal axis at their corresponding x positions and accompanied by those at the other locations along the x-axis. The steepness curve that is drawn over that top is better known as the function's derivative dn over dx. It follows the same course as the function itself, but its magnitude is scaled down by the factor 0.69. This proportionality is specific for exponential functions. No other mathematical function possesses such a property. We consider a general exponential function f of x equals a to the x, in which a is the function's base. 2 points are indicated on its graph, horizontally spaced delta x apart from each other. The red one is located at position x on the horizontal axis and the green at x plus delta x. Through both points, an intersection line across the function is drawn. The vertical position of both points is given by the function value at either location f of x and f of x plus delta x respectively. The vertical distance between the two is referred to as delta y. The intersection line crosses the coordinates of both points. For the red one, these are x and f of x, and for the green, x plus delta x and f of x plus delta x. The intersection line's slope, that is delta y over delta x, equals therefore the vertical distance f of x plus delta x minus f of x divided by the horizontal distance delta x. If the two intersection points close into each other by having delta x decreased, the slope of the intersection line will change. As soon as both points approach each other closely in the limit case, that is when delta x becomes infinitely small, the intersection line approaches the tangent line to the function at location x. Here, this tangent line is referred to as f prime of x. The derivative dy over dx, that represents the slope of this tangent line, is therefore the limit for delta x going to 0 of the intersection line's slope delta y over delta x. Thus, the derivative equals the limit value of the difference between the function values f of x plus delta x and f of x over the horizontal distance delta x for delta x approaching 0. By substituting the function's equation f of x equals a to the x into this generic expression, the derivative of a to the x is found. The limit for delta x going to 0 of a to the power x plus delta x minus a to the x over delta x. Next, this result is further elaborated. In the numerator, the term a to the power x plus delta x can be written as a to the x multiplied by a to the delta x. As a consequence, a to the x can be factorized from this numerator and taken apart from the remaining fraction. Notice that this factor a to the x serves as a mere scaling factor of the fraction the limit is taken of, since it's not depending on delta x. Therefore, we may just as well postpone that scaling operation until after taking the limit. So the factor a to the x is moved outside of the limit operation. The resulting limit operation will yield some value that's only depending on the function's base a. Later we will find out what it actually means, but for now just the fact that it yields some constant value is sufficient for our purpose. The conclusion that can now be drawn from this elaboration is that the derivative of the exponential a to the x equals some base-dependent constant times itself. Or, in other words, the derivative of an exponential is proportional to the function itself. The attentive viewer may have noticed that this is due to the fact that a to the power x plus delta x can be written as the product of a to the x and a to the delta x, allowing a to the x to be factorized and taken apart. That property is exclusive to exponentials. An estimation of the numerical value of the limit operation for certain values of a can be found by evaluating the expression for various small sizes of delta x. If 2 is chosen for a, and 10 to the negative 3, 10 to the negative 6 or 10 to the negative 9 respectively for delta x, we observe that the first 3 decimals of the result don't change. So we can safely assume that the limit value is roughly 0.69. Likewise, if a is increased to 2.5, the limit value becomes approximately 0.92, and for a equals 3 it rises to 1.1. To further investigate the way the relation between an exponential function and its derivative depends on the base number, a few graphs will be plotted for being compared to each other. The target is to find a value for the base for which the derivative becomes equal to the function. The first value that is assigned to the base is 2, which value we've already seen in the epidemic example in the beginning of this video. For this case, the derivative has shown to be smaller than the function itself by the previously mentioned factor of approximately 0.69. It's reasonable to expect that by increasing the base value, causing the function to become steeper, the derivative will be enlarged. Indeed, raising the base to 2.5 has the function's steepness significantly increased. Although its derivative is still smaller than the function itself, with a value of approximately 0.92 for the proportionality factor, the difference has become way smaller. Being on track, once more the base is increased, this time to 3. But now we have overshot the target, as the derivative appears to be some 10% higher than the function itself. This experiment leads to the conclusion that somewhere between 2.5 and 3 there must be a value for the base a that will have the derivative become equal to the function. This number, the value of which is yet to be found, is designated by the symbol e after its inventor, the Swiss mathematician Leonhard Euler. Indeed, using this for the base of the exponential will cause its derivative to completely coincide with the function itself. This brings us to the definition of e. It is the number that, when used as the base for an exponential function, will have its derivative made equal to that function. There exists another definition, originating from compound interest calculation in the financial world. It can be proven that it is consistent with our definition, but that requires knowledge of Taylor series expansion. As we don't need it for our purpose, we will leave it at just mentioning it. In section 2 of this video, from our definition, quite an accurate value will be found for e, using a rather simple, intuitively understandable iterative procedure. For the time being, we'll do with its rounded value 2.72. Before diving into the way of obtaining e's value, a few related items will be discussed. At first comes a brief recapitulation of logarithms, the inverse of exponentials. Like an exponential, a logarithm possesses a base number, the value of which may be variant. The graph on the left depicts the function y equals 2 to the x, the base 2 exponential that was already shown several times before. By mirroring the picture with respect to a 45-degree line, the horizontal axis is exchanged with the vertical. Thus the graph of its inverse function, x equals the base 2 log of y, is obtained. The logarithm is the power the base must be raised to in order to return its argument value. A numerical example. Since 2 to the third equals 8, the base 2 log of 8 equals the base 2 log of 2 to the third, which is 3. Notice that the logarithm operation cancels the exponentiation when both have their base in common. A commonly occurring value of the base is 10. The course of the function y equals 10 to the x is a lot steeper than the previous one. Accordingly, its inverse base 10 log of y operation does the opposite. Since we humans have 10 fingers, we are accustomed to use 10 as the base of our number system. This is therefore the default base for the logarithm operation. For this case, also a numerical example is presented. as 10 to the power 9.2 equals roughly 16, the log of 16 equals some 1.2. Likewise, but that's way off scale in the graph, the log of 1000, that's the log of 10 to the third, equals 3. It's all about e here, so this is the eventual value for the base to be explored in the form of the function y equals e to the x, together with its inverse, x equals the base e log of y. Because of the specific properties of e, the base e logarithm was given the special name natural logarithm, abbreviated to ln. One more connected numerical example. Since e squared equals about 7.39, the ln of 7.39 yields approximately 2. Now the relation between e to the x and any other exponential is examined. Because a logarithm is the inverse of an exponential, both operations will cancel out each other. When first the ln of a is taken, after which e is raised to that as its power, the result is a again. Because of this, a to the x can be written as e to the ln a times x. That is e to the power some constant times x, the constant being the natural log of the exponential's base a. Thus, any exponential function can be readily expressed in terms of e to the x. A few example functions are shown in comparison to e to the x. First, 2 to the x, that equals e to the ln 2 times x, or about e to the 0.69 times x. Next, 3 to the x, which is approximately e to the 1.1 times x, and finally 10 to the x. Notice that the horizontal axis is scaled by the respective factors 0.69, 1.1 and 2.3, causing the steepness of the function to be increased accordingly. Up to this point, only rising exponentials have been considered, the exponent of which is positive. When the value of the exponent becomes negative, the function will decay with advancing x. For instance, 2 to the negative x, which is equal to a half to the x, forms the mirror image of 2 to the positive x. Likewise, e to the minus x, that is 1 over e to the x power, forms the mirror image of e to the x. In comparison with that, e to the minus 2 times x has its horizontal scale shrunk by a factor 2, and decays therefore twice as fast. We just saw that the generic exponential a to the x can be written as e to the power x times ln a. Therefore, the derivative of a to the x with respect to x is the derivative of e to the x times ln a. According to the chain rule of differentiation, that equals the derivative of the power of e, which is equal to the function itself, times the derivative of its exponent, x times ln a. In this expression, the factor e to the x times ln a can be written back as the original a to the x, while the derivative of x times the constant ln a with respect to x simply equals that constant ln a. A few minutes ago, we found that the derivative of a to the x equals a to the x times the limit for delta x going to 0 of a to the power delta x minus 1 over delta x. That means that ln a must be equal to that limit value. Obtaining its value by means of the Taylor series expansion is, however, beyond the scope of this video. A few numerical values of ln a that could be found that way. ln 2 is approximately 0.69, ln 2.5 about 0.92, and ln 3 some 1.1. These particular values were already seen before in the form of the vertical scaling factors between the trio of exponential functions and their derivatives, the definition of E was reasoned from. This brief summary brings us to the end of episode 1. From the course of an epidemic, the generic exponential function a to the x was introduced that possesses the all-important property that its derivative is proportional to itself. The definition of Euler's number E was found by requiring that the exponential's derivative becomes equal to the function itself. Next, logarithms were recapitulated, of which the natural logarithm is the inverse operation of the special exponential function e to the x. And from that we found that the proportionality factor between a generic exponential a to the x and its derivative equals the ln of its base a. Please hit the like button if you find this video informative, and I hope you're interested in the next episode as well.